Howdy, and welcome to Lesson 1 about vectors and vector addition. Okay, so what are vectors and how do we actually do mathematical computations with them in something which we call vector addition? Well, to describe a vector, it's first important to understand a lot of the physical quantities that we generally work with on a regular basis. So, for example, some physical phenomenon we can describe with just a single piece of information. So the temperature of the house, for example, can be described with one piece of information, right? Maybe you can say that the temperature of the house is 76 degrees. Or you could describe the speed of a vehicle with one piece of information. You could say the speed of the vehicle is, say, 70 miles per hour, okay? There's only one piece of information that's being communicated in describing something like temperature or something like speed. So whenever we have a quantity that only provides one piece of information, or to say it another way, only requires one piece of information to provide the full description, we call those quantities scalars. Okay, so information or quantities that are described with one piece of information are called scalars. Okay, so temperature and speed of a vehicle, for example, are both scalars. They're only providing one piece of information when you talk about the temperature of something or you talk about the speed of something, okay? Okay, so that's a scalar, which is obviously not a vector. So the question becomes then, well, what is a vector, okay? We'll provide the definition of a vector more in just a little bit, but as you might already guess, based on the fact that a scalar provides one piece of information, a vector is a quantity that provides two pieces of information, or another way to say it, requires two pieces of information. Okay, so what does that mean? How do we think about a quantity that requires two pieces of information? Okay, so to describe that, let's think about an example, and let's suppose you're removing the lug nuts from your wheel to change a tire. And let's further suppose, and I highly doubt anybody actually ever does this, but let's further suppose that you read in your car's manual that the nuts are torqued to, say, 100 foot-pounds, or are tightened to 100 foot-pounds, right? So your car's manual specifies the tightening torque of the lug nuts to 100 foot-pounds. Okay, so that 100 foot-pounds, that's describing something which we call torque, and we're going to learn more about torque. We'll learn a little bit about it today, but we're going to learn a whole lot more about it later on when we dive deeper into our study of physics. Okay, but if all we know is that the tightening torque is 100 foot-pounds, that's actually incomplete information, okay? So to simply say the tightening torque is 100 foot-pounds is incomplete information. So what do I mean by that? Well, what I mean is the vast majority of lug nuts, or any nut for that matter, are tightened in a clockwise fashion. So if I have, for example, a lug nut and I put a socket on this lug nut and I apply a wrench to that socket, if I want to tighten the nut, then I turn it usually in a clockwise fashion. But there are some nuts albeit very few, that tighten in a counterclockwise fashion. And we refer to these types of nuts as reverse thread. So rather than being tightened in a clockwise fashion, they're tightened in a counterclockwise fashion. Okay? So you might have a nut, for example, that in order to meet the tightening specification has to be torqued to 100 foot-pounds, but it has to be torqued to 100 foot-pounds in a counterclockwise fashion. Okay? In other words, it's not enough to just tell me that it needs to be tightened to 100 foot-pounds. I actually need to know that it should be tightened to 100 foot-pounds in a counterclockwise fashion. Okay, so if we go back to our example of trying to unloosen or trying to loosen the nuts, say, on a wheel, and if for whatever reason the nuts on that wheel are reverse threaded, then there's a chance that if you don't know that when you go to loosen those nuts, that you're going to apply the torque in the wrong direction and actually be tightening those nuts as opposed to loosening them, okay? So to be precise, right, in order for the manual, the car manual, to be precise, the manual should specify both magnitude of the tightening torque so in our example, this would be the 100 foot-pounds number that we used, but also the direction. Of the tightening torque. And if it were a normal thread, that would be clockwise in our example. Thus, if you wanted to loosen that lug nut, you would know that you have to supply at least 100 foot-pounds in a counterclockwise fashion because you were told that the tightening torque was 100 foot-pounds in a clockwise fashion, okay? So, torque is only correctly specified with two pieces of information. And generally speaking, Those two pieces of information are magnitude and direction. Okay, so let's take another example. And in this case, this example is one that is going to start to make the connection for us to our ultimate development of vectors and vector addition. Okay, so let's suppose that we want to drive from College Station to the to the Dallas-Fort Worth Airport. And so when you look at a map and you, let's say something like Google Maps draw out the route for you, if this is, say, DFW, the airport, and down here is, say, for example, College Station, then really the fastest route is more or less the same for about the first half of the trip. But then at some point, you're going to have an option to take something which is called I-35 East, or you'll have the option to take I-35 West. And one route is a little bit longer than the other route, okay? So if you ask your friend how long it takes to drive from College Station to DFW, your friend might tell you that it takes 3 hours to drive from College Station to DFW at 70 miles per hour. So you were given a piece of information. You were told the speed that you need to drive in order to drive from College Station to DFW in only 3 hours. But when you drive from College Station to DFW, it takes you 3.5 hours. Even though you were driving 70 miles an hour. So what happened? Well, as you can imagine, your friend was perhaps assuming that you were going to take this direction along I-35 East, but you in fact took this direction along I-35 West, which is a little bit longer, and therefore, even though you correctly used the one piece of information that your friend gave you to drive 70 miles an hour, you were not given the second piece of information that you needed to know, which was the direction you were supposed to take. That is to go I-35 East as opposed to I-35 West. And so your friend didn't give you all the information you needed to know. You received one piece of information. In other words, you received the magnitude, but you did not receive the second piece of information, which was the direction. Okay? So, in this case, we have the idea of what we can call velocity. And velocity is a vector that includes two pieces of information. But before we get too far into that, we need to just recognize that in order to drive from College Station to DFW in 3 hours when driving 70 miles per hour, you actually needed two pieces of information where the one piece was speed, that is the magnitude, which in our example is the 70 miles per hour, and direction, that is east in our example. Thus, you needed more than speed you needed velocity. And we're going to define what velocity is in just a little bit. But another way to say this is you needed more than a scalar Remember that a scalar only has one piece of information. Instead, you needed what we call a vector. Okay, so let's go ahead and define what a vector is. A vector is a quantity that contains two pieces of information. In the physical sense, these two pieces of information are often magnitude that is how much there is of something, which in our example, that the two examples that we used was either the 100 foot-pounds or the 70 miles per hour. And direction. That is the orientation in the physical space which in our examples were either clockwise for our tightening torque example or east in our vehicle driving example. Okay, so earlier we said that, referring back to our driving example, we needed more than something which we call speed. We needed something which we call velocity. So what is velocity? Velocity is a vector that describes something's speed, or the rate at which it's changing its position, and direction. So a velocity necessarily includes two pieces of information, both the speed, or the magnitude at which something is changing its position with respect to time, and the direction at which the object is moving through the physical space. Likewise, we talked about torque, so we can just go ahead and close our discussion about torque for the present moment, where basically torque also is a vector that describes the magnitude of a force applied through a moment or what we call a moment arm, and the direction through which that force is applied. Okay? And so because torque has both the magnitude as well as the direction through which that magnitude is applied, torque is necessarily a vector. So we can give examples of both scalars and vectors. Scalars, of course, we're very familiar with because we've worked with those for several years and in everyday type applications. So examples of scalars in the physical world include things like the one example that we've already used, temperature. And we often use the letter T to indicate temperature, but not to be confused with the scalar magnitude of torque, which is also T. We'll talk about that in just a moment. Mass, where we use the lowercase m to indicate mass. Volume, which we use capital V with the little markings at the top of the V to help distinguish it from the magnitude of velocity, which is also V. And then pressure. Each of these quantities are scalar because only one piece of information is required to describe the various characteristics that they're describing. Examples of vectors include one that we've already talked about, of course, velocity. And to indicate velocity, we use the capital letter V. But then because it's a vector, we put this little symbol over the top, this half-headed arrow, if you will, to remind ourselves that this quantity also has the element of direction described by that quantity. And so velocity is described with the letter V with the arrow over the top. We also have torque, for example, which we use the letter T. And again, that's also a vector, so we put the directional symbol over the T for torque. And then finally, force is another vector that we'll talk about in physics. And again, we use the letter F with the vector symbol over the F to indicate that force is indeed a vector. Okay, so now that we have some idea about the notion of vectors, we now need to be able to do useful things with vectors. Particularly, we need to be able to mathematically compute vectors. For example, we might need to compute the velocity of one vehicle that happens to change its velocity at a certain time, and we might want to know what the change in velocity is, and we have to have a means to be able to compute that, okay? So discussing about vector computation, we need to first emphasize that you can't simply add vectors in the similar way that one would add scalars. So, for example, if you had 10 kilograms of oranges in a bag, and then you were to add 3 kilograms of oranges to that bag, you would then have 13 kilograms of oranges in your bag. Remember that mass is a scalar, and so you take 10 plus 3 with simple arithmetic addition, and you get the result of 13 kilograms. But we can't do that with a vector, okay? So, for example, if you were to say, that a car initially going 30 miles per hour to the east changes its velocity to 35 miles per hour to the northeast. It's not correct to simply say the vehicle changed its velocity by 5 miles per hour. In order to correctly characterize how the vehicle changed its velocity, not only would you have to determine the change in magnitude, but you'd also have to determine the change in direction. And so the change in velocity of the vehicle is both a magnitude component as well as a direction component, okay? Okay, so how do we actually define this, and how do we come up with a practical means of being able to calculate changes in vectors and do simple things such as vector addition, okay? So to explain vector addition, we introduce two concepts that will be pervasive in our study of physics. The first concept is what we refer to as particle motion, and the second concept is what we call displacement, which itself is a vector. And we'll talk more about both of these concepts, including especially displacement, much more as we go on. Okay, so first let's try to understand what is meant by this idea of particle motion and why is it so important to us in the study of physics. Okay, well, first of all, you can think of particle as basically the smallest, simplest element or component of the physical world that can actually move, right? Can undergo displacement, can have velocity, can have acceleration, can be subjected to forces, and all of the other things that we're going to study in physics this semester, okay? If you need something a little more tangible to think about what a particle might be or how you might think about a particle, imagine instead a pool table. Okay, so many of you have seen a pool table before. You have a certain length, you have a certain width, okay? And let's suppose that we split the table lengthwise in half, and we also split the pool table widthwise in half, And what I'll do is I'll simply say that the split of the table lengthwise is our y-axis, and the split of the pool table widthwise is our x-axis. And of course, we're looking down on the pool table from above, right? This is what we would call a top view of the pool table. And suppose that we have a ball, a pool ball, which will soon transition our terminology to, say, particle, right? So you can think of pool balls as being particles. And suppose that this ball exists at some initial location, which we're going to call P1, where P stands for point. Okay, so this is point number 1, where the ball exists at point number 1. And let's suppose that after some period of time, the ball relocates, right, in some fashion. We're not going to worry about how it does this. We're just going to know that the particle or the ball, the pool ball, moves its location to a second point, which we're going to call point 2. Okay? Okay, so we can recognize that the ball or the particle moved its location or it's been displaced. Okay? Now let's further suppose that the pool ball, rather than having relocated itself to position 2, to point 2, let's instead suppose that it moved itself to position 3, which we're going to call P3, point 3. So again, the ball moved from point 1 to point 3, but notice that point 3 is a different location than point 2. So clearly, the displacement of the ball from its initial point consists of two pieces of information. There's the actual distance that the ball traveled as it went from point number 1 to point number 2, or as it went from point number 1 to point number 3. And there's the direction that the ball moved as it went from point number 1 to point number 2. And in fact, in this case, it's actually that direction that distinguishes the ball's motion, its displacement, to be different as it moved from point 1 to point 3. In other words, the ball takes a different direction if it goes from point 1 to point 2 than if it goes from point 1 to point 3, even though the actual distance that the ball travels, the length of that travel, if you will, is the same. The direction is different, and of course you can see that because point 2 and point 3 are necessarily different from each other. So what this example highlights is that displacement, that is the motion of the pool ball, or more generally, using physics terminology, the motion of the particle, or the displacement of the particle, is a vector. It requires two pieces of information to be described. We require two pieces of information to describe the displacement of a particle as it moves from one point to another point in space. Okay? So, the displacement is a vector that describes both the length of travel of the pool ball or particle, right? Remember, we really want to think of this more as particles rather than pool balls, as well as the direction of travel. And we can say, of course, for example, if we describe the length of travel from P1 to P2 as L. And you can kind of see that in the drawing because this is being written on a grid, but that distance between P1 and P3 is the same, which is also L. So L, the length between P1 and P2, which is L, is the same as the length between P1 and P3. But clearly, the particle is not at P3 when it's at P2. So displacement requires two pieces of information that is magnitude and direction to properly characterize the ball's location, the particle's location. So we can then go ahead and define the vectors between P1 and P2 and between P1 and P3, and we'll define the vector between P1 and P3 as vector A, and the vector between P1 and P3 to be vector B. So vector A is describing the length and direction that the particle takes as it goes from P1 to P2, and vector B is describing the displacement the particle takes, the length and direction, as it goes from P1 to P3. So in words, what I just said is the vector between P1 and P2 is A, vector A, and the vector between P1 and P3 is vector B. And of course, we've already established that vector A does not equal vector B. Because even though their magnitudes are the same, their directions are different. So, we've defined a vector, say vector A, which describes the displacement of a particle as it moved from location P1 to location P2. And we've defined a second vector, vector B, which describes the displacement of a particle as it moves from P1 to P3. And of course, because P2 does not equal P3, that necessarily means that vector A does not equal vector B, despite them both having the same length. Okay? Okay, so we can introduce two new locations to try to help us understand a bit more about this idea of vectors being the same or vectors being different. So let's introduce two new points. We'll introduce point 4, which is a little bit higher on the grid from point 1, but along the y-axis. And I have to go a little bit outside of my pool table here because I wanted to have the same difference from P2 with this new point that P4 has above P1. And so we'll define P5 to be the same number of units above P2 that P4 is above P1, but along the same axis as P2. Okay? So clearly, the vector between P4 and P5, which we're going to define as vector A prime, vector A prime clearly has the same length as vector A, but it also has the same direction as vector A, even though it's going between two entirely different points on the same plane. Because vector A prime has the same magnitude and direction as vector A, we say these two vectors are equal to each other despite being in different locations along the plane. Okay, so let's go ahead and summarize this in words. So we introduce P4 and P5 and define A prime, vector A prime, to be the vector that is the displacement between P4 and P5. Note, as we discussed, that A prime, vector A prime, is in the same direction and has the same magnitude as A. Consequently, because they have the same direction and the same magnitude, even though P4 does not equal P1, and P5 does not equal P2, vector A is equal to vector A prime. And again, that's true since their directions and magnitudes are the same. Okay, so we can also say if you take a look at vector A and vector A prime, it's clear that they're parallel to each other, okay? And so we can say A vector A and A prime, vector A prime, are parallel but only because their direction are the same. In other words, two vectors are parallel if their directions are the same regardless of their magnitudes. Okay, now let's suppose we introduce another vector and we're going to call this new vector B, vector B. And I'll draw vector B for you in just a moment. Oh, excuse me, I'm sorry. We're going to call this vector C. So I'll draw vector C for you in just a moment. That describes the displacement of a particle between point 1, P1, and a new point that I'll draw in just a moment, P6. Okay? And we're going to suppose the magnitude of this new vector is the same as that of vector B, but its direction is opposite of vector B. So if we take this information that we just described and we go back to our little diagram up here, so we're going to introduce a new point P6, and we're going to let the vector C describe the displacement between P1 and P6, and the magnitude of that vector will be the same as the magnitude of B, but it's in the opposite direction of B. Okay, so that means that P6 is going to be up here in quadrant 2. So we have, quadrant 3. Okay, quadrant 2. Sorry about that. Okay, so P6 is going to be up here in quadrant 2 with the same magnitude as vector B. And so P6 will be located here. Same magnitude as vector B, but the opposite direction of vector B. And vector C is this vector that describes the displacement of the particle from P1 to P6. Okay? Same magnitude, opposite direction. Okay? So in this case, we say that vector C is the negative of vector B. That is, vector C is the negative of vector B, since even though the magnitudes are the same, the direction of C is opposite the direction of B. Okay, so, and just like earlier, we said that vector A prime was parallel or is parallel to vector A, we can say that vector C is anti-parallel to vector B, but again, only because its direction is opposite. In other words, the anti-parallel of a vector has an opposite direction regardless of the magnitude. So vector C is the anti-parallel of vector B, but only because its direction is opposite. In other words, two vectors are anti-parallel if they have opposite directions regardless of their magnitudes. Okay, so we've talked a lot about magnitude and direction, and we have some sense as to how one vector can equal another vector, or how one vector can be the negative of another vector. But we now need to really understand what we mean when we say the magnitude of a vector and the direction of a vector. Okay, so the magnitude of a vector is usually of chief interest so we will often specify the magnitude as the unvectored notation of the quantity. So, for example, the magnitude of velocity which is what we call the speed of something, so whenever we refer to the speed of something, what we're really describing is the magnitude of the velocity vector for that same thing. But anyway, the magnitude of velocity is just v, right? We use v to indicate velocity, and if it's the vector of v, we put the directional symbol over the top of the v, but if it's just the magnitude of the velocity, we leave that vector symbol off the top of the v. Likewise, the magnitude of the vector force is just F, and the magnitude of the vector torque is just T. And so the notation that we'll use for, say, velocity, right? So if we say the magnitude of the velocity vector is equal to just v, and we'll also oftentimes describe that as the two parallel bars that we often use to indicate absolute value of the vectored quantity. And so in this case, the magnitude of velocity vector is the two parallel bars surrounding the velocity vector notation. Okay, so these two elements on the right-hand side are both commonly accepted ways of indicating the magnitude of a given vector. Okay, so finally, we can now use this information to actually be able to do our vector addition. So we can describe what vector addition is, okay? So we know that a vector contains information about magnitude and direction. So when we talk about vector addition, it really only makes sense to talk about it in terms of addition as opposed to, say, subtraction, or where we might take something away from the vector, okay? So let me just write that down real quickly. So since a vector contains information about magnitude and direction, it really only makes practical sense to discuss vector addition since any vector that takes away from another such as vector subtraction would occur through the addition of the vector's directions. And you'll get a chance to see that in one of the examples that we have coming up here. Okay, so how do we visualize vector addition, and what exactly does that mean? Well, let's return to our pool table example and draw our XY plane. And let's suppose that we have a vector, and we'll call this vector A, that looks perhaps something like this. And then, say after the particle displaces along vector A, perhaps then it displaces along vector B. And the question is, what is the resulting location after undergoing these two vectors? Well, what we find is that we can actually determine what we call a resulting vector, which we can draw from the same starting point of the first vector, vector A, to the final point of the last vector, in this case, vector B. And that will describe for us the same motion of the particle in a resultant fashion. And so this third vector we would call vector C. And we can basically show that vector C is described as the addition of vector A plus vector B. And if you just happen to note here and think back on those happy days of trigonometry, you can see that there's a right triangle that gets scribed with really any one of the vectors, but for the purposes of this discussion, specifically vector C. And so we have a right triangle, and we can now essentially note that ultimately the particle moved a certain distance in the x-plane, and it moved a certain distance in the y-plane. And so there's an x displacement and a y displacement. And so we could determine the magnitude of C as simply using Pythagorean's theorem, the displacement in the x direction squared plus the displacement of the y direction squared, and that sum, the square root taken of that sum. Just a manipulation of Pythagorean's theorem. Likewise, we can define angle theta, where now with theta and the magnitude of C, so the angle of C, theta of C, and the magnitude of C, we can in fact describe exactly the location of the particle after it undergoes vector A and vector B. And so we can determine theta using, again, our trigonometry, where the tangent of theta is the opposite side, in this case y, divided by the adjacent side, in this case x. And so we can solve for theta c directly by doing the inverse tangent, sometimes called the arctangent, of the opposite side y divided by the adjacent side x. And of course, if you already know what your magnitude c is, you can also calculate c using sine, or the inverse of sine, which is the opposite side divided by the hypotenuse, magnitude c. Or you can use cosine, the inverse cosine, which is the adjacent side divided by the hypotenuse, the magnitude c. So you'll want to remember these relationships because you will consistently use these relationships, and we'll show this more in just a little bit, but you'll consistently use these relationships whenever you're doing any kind of computation with any type of vector. Okay, so this last example, this example that we just looked at right here, highlights for us the concept of what we call vector components. Okay, so what are vector components? So if we take a look at another vector on our xy plane, and suppose we call this just some random vector A, based on what we saw above with vector addition, where we can essentially have just vector A and vector B, we can essentially describe this by locating A and B really anywhere in the plane, so long as we start with the same initial spot and have the same final spot. But even in those cases where we don't do that, as long as the magnitude and direction of A is the same and the magnitude and direction of B is the same, we can locate them really any orientation relative to each other. And so what we can do with that is we can define the components of a vector along the unit axes where, for example, this could be described or defined as vector A in the x direction, in the y direction, and this can be described as vector A in the x direction. And we can simply show that vector A is the summation, the vector addition of vector A in the x direction plus vector A in the y direction. And so we call vector AX and vector AY the component vectors of A. So vector AX and vector AY are the component vectors of vector A. Okay? And the reason why they're called this is because the direction of the two vectors are along the primary axes. So because they're inherent to the two primary axes, we can say that the magnitude of component vector AX is the magnitude of A in the x direction and the component vector, or the magnitude of component vector AY is the magnitude of A in the y direction. And we would call these two magnitudes, respectively, AX for the magnitude of the component vector AX in the x direction, and AY, the magnitude of the component vector AY in the y direction. And so AX, the magnitude of component vector AX in the x direction, and AY, the magnitude of the component vector AY in the y direction, are called the components of vector A. Okay? And so note that they're called the components. They're not called the component vectors because at this point we've made them just the magnitude, just one piece of information of vector A. And so AX and AY are both scalars, okay? Whereas vector AX and vector AY are both vectors. They include both magnitude and direction, but when we take the magnitude of each of those component vectors, we then just get the components, which are the scalar magnitudes in each x and y direction of vector A. Okay, so now things start to get really easy when it comes to vectors and how we actually compute vectors. So we can determine magnitude AX, the scalar AX, and AY if we know the magnitude of A and its angle relative to a common reference point. By the way, having said that, in other words, having said we can determine AX and AY if we know the magnitude of A and its angle relative to a common reference point, that's simply just another way of saying that we know vector A. If you know the magnitude of A and you know its angle relative to a common reference point, in fact, you know the vector A. So we can go ahead and draw this on our XY plane. And let's suppose that this is vector A. And just to make this simple in our discussion here, we're going to say that this is the magnitude of A, and this is the magnitude of AY, and this is the magnitude of AX. And if we know, for example, the theta, the angle of A, then we can simply say that the component in the x direction of vector A is equal to the magnitude of vector A times cosine theta, which is also equal to just A cosine theta, and the magnitude of component y of vector A is the magnitude of vector A times the sine of theta, which is, of course, equal to A sine theta. And again, we're simply relying on trigonometry here, where we're solving for component AX, which is, if we, of course, take the cosine of theta is the adjacent side, which is component AX, divided by the hypotenuse, which is the magnitude of A. And so that's where we get this equation. And likewise, if we take the sine of theta, well, that's the opposite side, which is component AY, divided by the hypotenuse, which is the magnitude of A. And so that's where we get this equation here to solve for AY. Likewise, if we know the components of a vector, we can determine the vector itself. So again, if we draw our little diagram, our coordinate plane, and suppose this is vector A, that which we want to find, and we know magnitude AY, and we know magnitude AX, then we can say that the magnitude of A is equal to the square root, again using Pythagorean's theorem, of component AX squared, magnitude AX, plus component AY squared. And of course, theta is equal to the inverse tangent, or the arctangent, of our opposite side, AY, divided by our adjacent side, AX. And again, these equations you will use regularly and consistently as you work with vectors. So now that we've learned how to manipulate vectors or describe them both in vector fashion as well as in component fashion, and recognizing that we now know how to do vector addition, it becomes very easy to do vector addition when we consider the vectors in terms of their components. Okay, so describing a vector with its components makes it easy to add two or more vectors. When adding two or more vectors, one simply adds the component vectors or the components with the appropriate sign included as needed to capture the influence of direction and this, of course, is all to get the resultant vector. So what I mean by that, again, looking at our coordinate grid, suppose this is, or suppose we have vector addition with vector A, and we add to this vector B, and we want to know what the resultant vector is through the addition of these two vectors, vector C. So again, recall that vector C is vector A plus vector B. But what we can do is we can break each of the two vectors into their component vectors, where we have vector AX, or excuse me, vector AY, and vector AX. And likewise, we have vector BX and vector BY. And by adding the similar component vectors to each other, we can determine the resultant vector C. And so vector C would be component vector AX plus component vector BX plus component vector AY plus component vector BY. And so I put parentheses around the two component vectors, AX and BX, and AY and BY, because it's between these two vectors, AX and BX, that you would actually do an arithmetic sum, or between the other two component vectors, AY and BY, where you would do an arithmetic sum, okay? And so using this relationship, you then can very easily do vector addition. Okay, well, this is everything that you need to know about vectors at the present moment. If you have any questions, let me know. Hope you enjoyed the lesson.